Hey everyone, so we're going to continue our discussion about simple harmonic motion, and we're going to focus on springs. I said before that a lot of the stuff that we're going to talk about when it comes to simple harmonic motion, we're going to pretty much focus on spring motion and objects that are connected to springs oscillating because of that. And with that information, we can actually very easily translate that conceptual understanding over to the other types of simple harmonic motion. So like pendulums kind of will end up working the same similar way. Objects moving in circles can kind of be represented similar ways. So this will be used as a simple, easy setup dealing with the springs so that we can uh, come up with concepts to apply to some more complex harmonic motion. All right. Now a lot of this is going to be a recap from what we've done before. So for I think it's this video and the next video, I'll end up pretty much covering a lot of similar stuff from springs as I have in a previous in the energy unit. So we said before that when a spring is in harmonic motion, the force that's acting as the restoring force, the main driver that's constantly pushing the object back to equilibrium, resulting in the periodic motion, the force here is the spring force. So regardless of whether it is acting horizontally, vertically, or even on an incline, uh, the spring force is going to be the main driver towards that restoring force. Now, this force was actually kind of, I don't want to say discovered, but was developed, and they went into more detail from the scientist Robert Hooke. He designed an experiment where he ended up placing masses onto different springs and measured how long it was. He did multiple trials and graphed his data because he was a good scientist. And he found that there is a linear relationship between the force that the spring that can be exerted onto the spring and how long the spring elongates. So if you apply 5 newtons of force, it would elongate a certain distance. If you doubled the force that you applied, it would double the distance it elongates. And he also found that it worked the same way for compression. So it didn't really matter whether it was being elongated or compressed. The relationship between the force and displacement were the same. One thing he did find out was that even though this relationship was the same for all springs for a certain point, he did notice that each spring had a different slope. So comparing the slope to what the springs actually physically felt like, and what he experienced with the springs, he decided to call the slope the spring constant, as it was a description of a characteristic of the spring, that it was just a natural part of the spring, that it represented how rigid the spring was. The higher the spring constant, the more rigid, the more stiff, the harder it was for the spring to flex, while a low spring constant meant that it was very easy to pull it around. So a good example is slinkies typically have extremely low spring constants. It requires barely any force in order for you to pull them a good decent apart, while something like a car spring, uh, that one would be considered a lot more rigid of a spring because it requires a lot more force for it to move somewhat noticeably. So from the relationship, so because of the linear relationship between force and spring constant, he knew that there were in the equation there was no exponents. They're both on opposite sides of the equal signs in the numerator, and because they were linear, they had a slope which was defined as the spring constant. So that led to this equation: f of x equals kx. F of x, as we've mentioned before, that's the spring force. That's the force that the spring is applying onto the object. K is our spring constant, and x is being defined as the change in the spring length. One thing that I don't know if I explicitly mentioned it, because I don't know if I went into too much detail with this equation last time, but when we talk about the change in the spring length, it's tied to the force that's applying it. So, for example, if we start off with a spring that has no forces acting on it, and then a 20 Newton force is applied, then we're going to measure the change in length from that original length, the unstretched length essentially, to its new length. However, if instead we had a scenario like this, where we had a spring that was, we'll just make it 10 centimeters long, then a mass is attached to it, bringing it to 20 centimeters long, and all of a sudden we know that another mass is attached to that original mass, and this was a force of, let's say, 10 newtons, bringing this to 30 centimeters. When we do this equation, I don't have to start from the original length to this. I just have to worry about from when this force was applied. So the force was applied when it was originally at this location to this location. So the x in this case would actually be 10 centimeters. So it's just one thing to keep an eye out for, because if you actually try to do it with the original length, the way that I've written it, it's impossible to answer because I don't know what this mass is. And that's actually kind of one of the nice things about this equation is that you don't need to have it from the very beginning when the spring was on stretch. You just need to know when this force was applied to it, it changed this much. All right. So this is the equation. Now there is one thing that I want to point out is that it has these absolute value bars. Now there's one other equation that we've actually done that also had absolute value bars, and that was the frictional force equation. So if you recall, the frictional force equation was absolute value of f of f is less than or equal to mu absolute value of f of n. And if you recall what I mentioned about this, the reason they put these absolute value bars in is that um, while the magnitudes satisfy this equation, the values of these forces satisfy the equation, because force, the f of f and f of n are vectors, they carry a direction with them. Even though we don't put them in all the time, when we use this equation, technically this is f of n up equals blah, 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 and that this frictional force also has its own direction. If I don't include these arrow bars, what I'm saying is that their directions are the same. For example, F net equals ma. F net equals ma does not have any absolute value bars. Both force and acceleration are vectors. And because of the way this equation is set up, what it says is the direction of acceleration is also shared by the direction of the force. This becomes extremely important of an aspect when you go into college level physics, like actual more in-depth college level physics, but also with, I guess it would be, I think it's multi-dimensional algebra, where you can do math in, X, Y, and Z directions. In those cases, numbers, you can actually write numbers to have direction in them because they're vectors. Like I said, the term vector is actually a math term. And it becomes extremely important to whether or not the equation is saying that they're sharing directions or just that the values are satisfying a certain equation. So just as a recap, with the frictional force, the absolute values there are because those two forces are not in the same direction. And in fact, for these two, they're in completely different dimensions. The normal force, if it acts vertically, the frictional force has to act horizontally, and vice versa. In addition, if I know the direction of the normal force, and I know that the normal force acts up, I don't know the direction of the friction. I don't know. It could be to the left. It could be to the right. It really depends on the scenario. The direction of the normal force does not dictate whether the frictional force is left or right. All it dictates is that it has to be horizontal, perpendicular to it. So a similar thing applies here. The absolute value bars are put in here by the AP to remind you that these two are not in the same direction. That the direction of x, the how much it elongates and compresses, is different than the direction of the spring force, the direction that the spring is pulling or pushing an object based off of this change in length. Now, there is something a little bit weird about this absolute value. The reason why I think it's a little bit awkwardly put in here for this case is that in the case of friction, as I mentioned, these are completely perpendicular to each other, while in this equation, there is a relationship between their directions. In fact, the direction of x is always in the opposite direction of the force. If you pull an object to the right, so if you have a block that would normally be here, if you move it to the right, its position is going to be a positive value. It's going, consider this to be 0, the origin. We move it to the right, its position is in the positive direction. But because the spring force is a restoring force, it's going to try to bring it back to the equilibrium, so it's going to push it to the left. Vice versa, if I take this object and compress it, move it to the left side, again, the spring force is going to try to balance the equilibrium and move it and push it to the right. So these two are always in opposite directions. So a lot of times, if you look online or if you look in other sources, you might see the equation actually written like this. This is actually the much more common way that it's written, as f of x equals negative kx, because the direction of x is in the opposite direction of f. That's actually why the negative is put in there. This is going to play a part in probably not the next video or two, but in one of the sections where we start coming up with equations for the motion of a simple harmonic motion. So I'll try to bring this up later. For the most part, though, what this means is in a lot of cases, you can actually just ignore that negative for now. Just do the absolute values essentially when you do your calculations, and only worry about the negative when it comes to direction. So kind of like what we've done in previous force questions, where we ignore direction, we ignore signs in the equations, and we just worry about directions when we do FBDs. We take into account the direction right from the beginning, and then we don't have to worry about it in our calculations. All right. So this is a little animation that kind of shows the same idea. So again, you could see it as the animation plays, that as the object moves either in the positive direction or the negative direction, the force is always in the opposite direction. So again, this is why the force is commonly written with a negative sign in it. All right. There was one other thing that I wanted to talk about, and that was actually the fact that I was being a little hand wavy with Hook's relationship that he found. So he did find that the force and the amount that the spring is stretched was linear. However, he found that that only worked for a point. See, if you stretch a spring or a rubber band, as you know, uh, if you pull it just a little bit, it always returns back to its initial state. You can never tell that it was initially stretched as long as you don't pull it too far. But if you've ever played with a spring before, if you've ever played with a slinky in particular, you know that if you pull it just a little bit too much past a certain point, it starts getting deformed. What he ended up calling that area where all of a sudden it starts getting deformed, is called the plastic region. So there's a little section right about here where it ends up it stops being elastic, meaning it stops going back to where it's supposed to be. And that's where once you exceed the elastic limit, it starts getting deformed. And then if you continue to stretch it, it stops kind of stretching too far because it's starting to get warped a bit. But eventually it will end up breaking. So this is actually what the full graph looks like. Now you don't actually need to know this, but this is just meant for labs, because I want you to know that when you're dealing with springs, that you can't stretch them forever. I want you to make sure that you don't pull too much. Now, unfortunately, I don't think there is a real concrete way to figure out what the elastic limit is and when you're reaching the plastic region. So just keep an eye out for it and try to avoid having the springs, go all the way down to the table, or making sure that masses aren't hanging onto the springs for too long. While it probably won't deform it, I don't want to risk it. I want to make sure that I maintain these springs for as long as possible. All right. So let's practice this question. So pause the video, work yourself, and we'll go over in a second. All right. So this is a pretty straightforward question. They want us to know what the spring constant is. Again, we use the forces. So we have a weight being pulling the spring down. We have the spring force kind of balancing out. So when I do force equals kx, again, I'm dropping the negative in this case. I end up putting in my numbers. I need to make sure that I can calculate the force of gravity on this mass. So I multiply this by 10 to get 2.5 newtons, divided by 0.05 meters, and I end up getting that this is actually a typo. The spring constant is 50. I think I made that same mistake elsewhere. So the spring constant is 50 newtons per meter. All right. Here's the next question. Pause the video, work yourself, and we'll go in a second. All right, same idea. So again, we use the same equation, F equals kx. This time when we plug in the numbers, we don't have to do that same calculation for force, but now I have to try to figure out what do I plug in for x, because I have two lengths. Well, remember, x is the change in the spring length, so I take the difference between 1 and 0.5, so I get 20 equals k times 0.5, divide the 0.5 over, and I get k, the spring constant, equals 40. One thing I want to point out is while these numbers have the spring constant as fairly small, spring constants can go all the way up to hundreds to sometimes even thousands, depending on the spring. So don't think that this is an indication of the typical magnitude for a spring constant. All right. I'm going to leave it there. I want to save some of the other stuff that I want to talk with springs in other videos to try to break it up. So if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.